Welcome everyone to Lecture 5, Part 2 on Entity Relationship Diagram. Today we will continue our journey into the ER modeling world. If you remember from Part 1, we discussed how to model real-world data using entities and relationships. Now we will move deeper into how to represent more complex situations in our diagram. We will cover weak entities, extended ER features, and how to design a university database. This forms the foundation for converting models into relational schema in later parts. As we go, I will explain the notation and the meaning behind each symbol. These concepts help ensure our database design is complete, accurate, and flexible. So let's jump in and begin with a quick refresher on entity and relationship sets. Please feel free to ask questions in the mid of the lecture or discussion forum as we proceed. Let's start. How entities are shown in an ER diagram. Each entity set is drawn as a rectangle, and inside it we write down its attributes. Among those attributes, the one or more that uniquely identify each entity are underlined. For example, in a student entity, student underscore ID might be the primary key and would be underlined. This graphical method helps us quickly see the structure and important part of each entity. It is clean, standardized way of representing data that avoids ambiguity. Remember, an entity is like a noun, a thing. We are storing data about such a person or a course. Attributes are like property or characteristics of that noun. When designing your diagrams, always make sure primary key are clearly shown. Let's now look at how relationships are represented between these entities. Relationships connect two or more entities and are shown using diamonds. Think of relationship as verbs. They describe how entities are related. For instance, teacher or instructor relationship might connect an instructor and a course. Inside the diamond, we write the name of the relationship. This is the name of the relationship, means instructor, advisor, student. Instructor is the advisor to student. The diamond is then linked to the entities it connects using lines. Here, what is the relationship between instructor and the student? Student get advised from the instructor, or instructor is giving advice to the student. Relationship can have their own attributes, like the date an instructor taught a course. In that case, we put the attribute inside the diamond as well. This helps us model real-world connection in a structured way. Remember, both the existence and nature of relationships matter in database design. Next, we will look at the idea of role in relationships. Sometimes an entity participates in the relation more than once. To distinguish these, we assign roles, labels that clarify each instance of the entity. For example, in a prerequisite relationship, a course is related to another course. Here, one plays the role of course ID and other play the role of prerequisite ID. To avoid confusion and make the relationship unambiguous, Roles are especially important when the same entity appears multiple times in a relationship. It's like saying course A is a prerequisite of course B, where both are from the same set. These roles are written next to the connection lines in the diagram. Using roles ensure clarity when diagram become more complex. Let us now look at how we represent constraint in this relationship. Cardinality constraint show how many times entities can be involved in a relationship. We use arrow We use arrows and lines to express these in ER diagram. A directed line, an arrow means one and an undirected line means many. For example, if each student has one advisor, the student side gets an arrow. This gives us a one-to-one relationship between student and instructor. If an instructor advises many students, that's a one-to-many relationship. So it's important to always ask how many of these can relate to how many of those. Correct cardinality is vital for database integrity and accuracy. We will now break down the one-to-many and many-to-one scenarios in more details. Let's take a closer look at them. In a one-to-many relationship, one entity set from set A is related to many from set B. Think one of instructor advising several students, very common in universities. Here, each student has at most one instructor, but an instructor can have multiple students. We show this by placing an arrow from the student to the advisor relationship. This tells us the direction of the one side. One-to-many is the most common pattern in real-world databases. It's essential to capture this correctly to avoid data redundancy or inconsistency. Pay attention to which side is one and which is many. It affects your schema later. The design decisions here directly impact database performance and correctness. Next, let's flip this and see what a many-to-one relationship look like. In many-to-one relationships, many entities from set A relate to one entity in set B. Imagine many students sharing the same advisor. In this case, many students to one instructor. It might sound like one to many, but if depends on which direction you are viewing. From the instructor point of view, they are related to multiple students, but from the student side, each student has only one advisor. We represent this similarly with an arrow pointing to the one side. Direction matters. It defines data constraints when we implement the database. These relationships must be well understood to maintain data accuracy. Don't confuse many to one with one to many. They are minor images or they are mirror images but distinct. Next, let's look at many to many relationship. In a many to many relationship, entities on both sides can relate to many on the other. For instance, student and instructors may be connected through project supervision. A student might work with multiple instructors. An instructor may supervise multiple students. These relationships can get complex, so we model them carefully. There are no arrows in this case. As you can see here, there is no arrow either on the student side or on the advisor side. Both sides are connected with plain lines. We must also consider the attributes of the relationship, like project topic or duration. Many-to-many relationship often require a separate table in relational design. Without this, we risk repeating data or creating inconsistencies. Understanding when to use many-to-many is critical in schema planning. Now let's move to the idea of participation. Whether every entity must be involved, total or partial participation. Participation tells us whether all entities in a set must participate in a relationship. Total participation means every entity must be involved. It's shown with a double line. Partial participation means some entities may not be involved, shown with a single line. This is partial participation and this is full participation. For example, every student must have an advisor. This is total participation. But not every instructor has to advise a student. That's partial participation. Participation affects our understanding of data requirements. It's like saying, is this relationship mandatory for every record? In database design, this can impact how we define foreign keys. If you miss this detail, it can lead to missing data or flawed logic. Next, we will add more precision using min-max notation. To express more precise constraint, we use min-max notation like 1, 1 or 0 star, 1, 1 or 0 star. The number before the dot is the minimum and the number after is the maximum. For example, 1 dot dot 1 means the entity must participate in exactly one relationship. 0 dot dot star means it can participate in any number including none, none to many or 1 to 1. This allows us to capture rule like a student must have exactly one advisor or an instructor can advise many students or none at all. This level of precision is crucial in enforcing business rules in your schema. It's also helpful when working with object-oriented models or UML diagrams. Understanding this notation gives you more control over your data model. Now let's look at special entities, weak entity sets. Notation to express entity with complex attributes. Here are the notations like ID, name. Name can be divided into first name, middle initial or last name. Then we have address. Street can be divided into street number, street name and apartment number. Then we have city, state and zip. This all makes address. Then we have phone number, date of birth and age. Age can be derived from date of birth. A weak entity can't be uniquely identified on its own. It relies on strong entity for its identity, like a section depending on a course. In diagram, weak entities are shown with the double rectangle, like we are showing here, the double rectangle. Third identifying relationship is shown with the double diamond, like this one. Inside the weak entity, the distinguishing attribute is underlined with the dashed line. The combination of this attribute and the key from the strong entity makes a unique ID. For example, section ID alone it's unique but with course ID it become for example section ID alone isn't unique but with course ID it become unique. Modeling weak entities is important when your data has dependent sub-entities. Missing this could result in data integrity issue. Now let's bring it all together with an example of a university ER diagram. ER or Entity Relationship Diagram for a University Enterprise. Let's see section by section, explaining the entities, relationship and how they interact with each other. This is typically shown to illustrate a high-level conceptual model of how data is related in a university setting. So what are the entities here? The first one is city, which are having attributes name, state. A city is the birthplace of a person. Person having attribute like last name and age. Appears twice, possibly indicating different roles. Example, student and professor. Next entity is student, subtype of person linked to city through the birthplace relationship. Graduate student through generalization or specialization. Course through the enrolled and planned relationship. Professor through the advised by relationship. Next we have graduate student, specialized form of student, possibly with added constraint or attributes. Next we have professor, subtype of person, attributes like tenure status and title, related to student through advised by and course through, taught by. Next entity is course. Course having attributes like title, description and credits, linked to student and graduate student through enrolled and planned, linked to professor through taught by. Next we have room with attribute number and building. Next attribute is time, having at next entity is time, having attribute day and hour. So what are the relationship we have here? First relationship is birthplace. Connects person to city, suggests where the person was born. Next is belongs to. Connects professor to person, could imply inheritance or organizational relationship. Next we have resident. Connects student to city. Student resides in a city, likely current residence, enrolled or planned. Connects student and graduate student to course, indicates course enrollment or planned future courses. Next we have advised by. Connects graduate student to professor, typically advisor-advisee relationship in universities. And the last one is taught by. Connects course to professor, indicates which professor teaches which course. The last one is meets. Connects course with room and time. Describe when and where the course meets. So what is the interpretation of this diagram? This diagram models the key elements of the university academic structure. Students enroll in and plan courses which are taught by professors. Graduate students have advisors. Each course has scheduled meeting time and rooms. People are linked to birth cities and roles like student or professors. Specialization like graduate student and clearly modeled. Thank you for attending this lecture. We will meet you in the part 3 of ER diagram.